Alright nerds, so let's talk about mass spectrometry. Now, as that is a pain to say, I'm going to call it mass spec from now on. Now, basically a mass spectrometer is an apparatus that measures the masses of isotopes. And these are isotopes of, also including, isotopes of molecules and molecular fragments. And molecules don't tend to be ionic, and it needs them to be. So what it does is it makes ions of all of these guys, of molecules and molecular fragments, by hitting them with electrons to knock electrons off. And if it knocks electrons off, you turn it into an ion, and then it can guide it and with a magnet. That's pretty cool. Let's have a look how it works. So basically, this is a schematic of our mass spec device right here. Now, the first thing it does is we put our sample in here and we ionize it. And basically there'll be a coil in here or an electron beam. But if you heat a coil up, it'll fire electrons off as well. So we pass it in here and it gets ionized. And it ionizes this by knocking electrons off, creating positive ionic molecules. And that's important. Then they are accelerated out. They're accelerated here, and they're all accelerated at the same rate, so they all have the same kinetic energy, and that's important. Then they are deflected. So they are shot through a slit here, along a narrow path, at a very, very low pressure. And as it goes along, it hits, there's a couple of the electromagnet here and here, which should bend it along the path. Now, when they do this, they're compared against standards, so we know what's what. So it bends it along the path this way. Heavier ions will land over here. Will land here or against there. But heavier ions will come this way. Middle level ionic molecules will come down this way, and really light ones will hit over this side because they'll be bent further by the electromagnetic field. Their momentum, because of their mass, won't be able to carry them along as fast. And we detect them as the beams pass through a machine, and they detect them electronically. So the ions hit it, they give it a charge, and it goes ping, that's where it is, which means it's on this point on the plate, therefore it is this mass. So larger molecules, this includes our organics, will also break into smaller fractions, and we can add these up to work out what the mass is, and we'll show you how that works in a minute. But this is another diagram of it. So we inject the sample here, they are so it gets heated to vaporize the sample. An electron source is firing electrons through, and so it's going to be vaporized basically, and the electrons will knock an electron off, which will make positive ions. It'll also make negative ions as well, but those won't be accelerated through the beam. So the particles are accelerated into this magnetic field, and then as they come down, we'll see that the field bends, and all the lightest will bend the most, the heaviest will bend the least, and in the middle, obviously there. So the base, they're being separated based on their mass charge ratio. Okay, and remember the charge of these guys is all 1, so it's mass to charge, which means whatever its mass is divided by 1. So that's really interesting too, which makes the graphing really easy. So we just basically get one with their molecular weights. Mass spec will often be joined and combined with other analytical methods, and the mass spectra are unique. Each compound will give an individual mass spectrogram, which we can then compare against. This is what it looks like. So this is the internal workings, right? There's your big magnet. Here's your acceleration and injection chamber. And here is your detector down here. Now, this is what it looks like when you're actually dealing with it. It's a very, very slick-looking machine. So let's have a look at the graph and how that works. Now, here we're not going to look at cyclopropane so much. We're going to look at carbon dioxide and propane. And the reason we're going to do this is because they have identical atomic mass. Well, close enough. So the y-axis is the relative abundance, so that's what there's most of, and the x-axis is the atomic mass. That should say, actually it's the mass to charge ratio, but it's mass divided by 1, so essentially this is the atomic mass. Now, the molecular weight of carbon dioxide is 44. You can see a big peak there, and there's a peak there at 44 as well, and that is propane. Now, the furthest peak to the right is called the molecular ion peak, or the M+. And it gives you the molecular mass of the analyte. That in itself is really interesting. See, this one here has a slightly smaller one. And that's because it's got less hydrogens than propane. The positive ionic molecules will often break apart in the mass spec machine, and that gives us these other peaks here, right? So what you can see is we've got our peak at 45, but some of it will break into one that's 16, which will be oxygen, and one that is 28, which will be, so half of it will be an oxygen, and then the other half will be a carbon and an oxygen joined together, the molecule fractures. But we add them up, it's the same as over here. And we get the same here. We've got different fractions. If we add certain two together, we would get 44. So this is what the carbon dioxide one looks like. So here's our relative abundance. There's the overall mass of 44. But we've got a mass to charge of this one here. So this is our positive ion. They're the ones which are detected. And it is 16. So this is when it fractures. And here is our other positive ion, which is 28. So you add those together, and that gives you your 44. And here is our propane one. For example, propane can break into all of these. So here's our molecular ion, that's at 44. And propane can break into 15, 43, 28, and 29. And we see these on the graph there. So that's how we read it. That's how we detect it. And that's what mass spectrometry is. I'm sure you've heard a lot of it over the years, and now you actually know what it is. I hope that makes sense. If it didn't, put any questions in the comments below, and we'll get back to you as quick as we can. Thanks for watching. Bye now.